since they are linear independent. Okay, yeah, they are linearly independent. That is true. So he's just elaborating on what we discussed yesterday. Yeah, we can do that, but yeah, we can that we can do that. So he's just changing the reference of axis from x and y to these vectors, but it's a topic that we can elaborate on more later. Okay, then. So we have uh, uh, different answers. It's a matrix is can represent points in R2. It can represent vectors in R2. It can represent system of linear equations, system of simultaneous equations. It can also represent a function having information where your uh, I cap and j cap, your unit vectors map to. So it can represent that as well. Okay, perfect. So after this, I have another question for you. Where and why do we use matrices? Can you enlist some applications for it? Where and why do we use this? Where do we use these matrices and why? I'm pretty sure some of you are familiar with some of the uses of matrices. So where do we use matrices? Anyone? Image processing, correct. That's one application of matrices. Another another answer. Projections for of what? Himanshu, you'll have to be a little more elaborate with your answers. Representing linear applications, yeah, that's where we that's something you can do with matrices, but that's not a use case for it. You can say we can solve system of linear equations. Uh, that's one way. Sparse matrices in data storage. That's true. That is correct. We use in data storage as well. What else? You were correct. We use it for image processing as well. We use matrices to solve system of linear equations as well. Projecting a vector to the plane. I mean, that's not a use case. That's an operation with matrices that we do. That's not a use case. What else? I'm pretty sure you guys must be aware of game development. You use matrices in game development as well. Vectors and matrices. Covariance matrix to fire finding relation between features. Oh yeah, correct. That's to forecast future trends in financial markets. Yes. Yes. Okay, perfect. We have enough applications, I think. Okay, we can move on to question number two. That is, what is a function? Define a function to me. Can anyone give me a brief definition of a function, then matrix transformation to change 3D scenes to 2D to show on screen? True, correct. That's one another application for it. Can anyone tell me what a function is? Yes, Jagrit, that's correct. We use matrices and vectors in 3D modeling as well. True. Can anyone tell me what a function is? I need quick answers for these questions, guys. These are basic questions that you've been studying since. It maps one matrix to another. Oh, I'm not talking about matrices here, my mate. I'm only asking what is a function. What is a function? What's the basic definition? We've been an expression, rule, or law that defines a relationship between one variable, the independent variable, and another variable, the dependent variable. Oh, I'm not asking for the book definition. It takes input, does some process with it, gives an output. Perfect. That's that's really nice explanation to it. something that's not bookish. I like that. It takes an output, does some process with it, something it does, we don't know, and gives an output. That is correct, Jagrit. I really like that answer. That's a function. A function is sort of like a black box. We give it input, it gives us output. Okay. So that's function. What is injective function? What is surjective function? What is onto function? What is in one-to-one function? Can anyone quickly tell me that as well? Onto and one-to-one. What is a onto function? What is a one-to-one function? I'm pretty sure you guys know these as well. One-to-one means mapping of two sets. Oh, that's a function. Function does mapping from one set to another, but that does not mean it's one-to-one. One-to-one for one input, you get one output. Oh, that's functions in general. You for one input, you get only one output. F of xy equals to f of y if x equals to y. That is correct. That means if you have same output for two function, then those inputs would be same as well. No two inputs give the same output. That is correct as well. No two inputs give the same output. That means for every input, you have a unique output. That's the key word there. For every input, you will get an output if it is a function. But for every input, you will get a unique output. Only then you can call it a one-to-one function. Is Rishabh here? I have the answer for his question. Okay. I'll wait for Rishabh to join in. Once Rishabh joins in, I'll see what I couldn't answer him yesterday. I have the answer for that. Yeah. So no two inputs give you the same output. That's one-to-one. What is surjective? Can anyone tell me what surjective functions are?
One quick question before we move to surjective functions.
Yeah.
So we just discussed injective function that for every input there is a unique output.
Correct.
That is to say, we are talking about two sets, the
Right.
input set and the output set. For every input, we have got a unique output.
Right.
But does
Right.
that mean that all the elements in the output is
Right.
mapped, or there are some vacant elements in the
Okay.
target set?
We'll come to it. We'll come to it. We'll come to it. We'll come to it. I'll just need a quick explanation, a quick definition for onto functions. Codomain will be equal to range, correct? That's one definition. What can be another definition for codomain? Sorry, not codomain. One onto functions. What can be another definition for onto functions? Quick answers, guys. Every element of B, there is at least one or more than one element matching with A. Correct. Matching with A, I think matching with B. Subjective. Every element of functions output is the image of at least one input. That is correct. That is correct. So every element in your codomain is actually mapped to some pre-image in the domain. So that's the subjective function. Okay, let's take same example that we took yesterday. Maria, you'll have to show your drawing skills and you'll have to make some boxes. So can you make a box there?
What's the question? What's the question?
Not a question. I'm going to explain something there. So you'll have to
Okay.
draw something. Make a box
Yeah,
there.
sure. Like this.
Yeah. Put 5 balls there. Yeah. Make another box. Just give me a second. In that other box, put 2 balls there. 3. Make it 3. Yeah. Perfect. Can you do? Can you match those balls to those the 5 balls to the 3 balls uniquely? Only one ball to one ball.
Question. Like I think people didn't understand. You need
Okay,
so
just do one thing. Just match those balls. I'll be explaining that. I'll be explaining that. We'll discuss everything. Don't worry. We're not jumping ahead. Just just map one ball to a unique ball. To yeah, make another box which has like uh, say three balls in the first box and five balls in the second box, and map balls uniquely. Hi, Pratmesh. Are you from Old Coders High? Or is this your first session? You're on mute, my friend. Yeah, hi. Mic is not working. Perfect. No issues. Are you from Old Coders High or is this your first session with us? Oh, right, right. Nice to have you. Nice to have you here. Today we don't have Vinay here. Usually Vinay is here and Ashik as well. So nice to have some old people here joining. Okay, perfect. So can you draw another box with say five balls and balls in another box? Five balls in the first box, three balls in the second box.
that's the first image, right?
Oh, pardon?
No, that's the first image itself, right? You want me to draw the
Oh,
first image?
again, again. I want five such cases. So you'll have to show your drawing skills again and again.
Page.
So five in the first, three in the second. And do one thing, map two of the balls from the first box to one single ball in the second box. Yeah. Do other two as well. Map two other balls to one single ball and map one single ball to one single ball. So you'll have to map the other one as well. Just map the one ball. Yeah, perfect. Now draw another box with three balls in the first, three balls in the second. Map two of the balls in the first box to one single ball in the second box, and one ball to the unique ball. One unique mapping and one 2-to-1 mapping. Oh, no, no. 2-to-1, 2-to-1.
Yeah, yeah.
Right. Draw one another box with three balls and three balls and do a unique mapping from each ball to each ball. Pratmesh, have you gone through the linear algebra 75? Okay, you haven't. Okay, no issues. Then we are going through linear algebra 75. Uh, this is just the beginning questions. So I'm being a little fast here, but for the later questions, we'll be spending some time on it. Yeah, perfect. So can anyone tell me the first case here, is this a function? Is this the first case? Is this a function? Right? Some quick answers. I'm pretty sure you all know this. Yes, this is a function. Can you elaborate a bit more why you think it is a function?
Anurag thinks otherwise.
Okay, and Rag thinks otherwise. And Rag, can you tell me why it's not?
Interesting. Somebody says yes, and another one says no. This is the most interesting thing that can.
Yeah, now this is becoming interesting. 1-1. Okay. One
Ah,
versus one. One versus one. 1v1. So, Jagdish, would you care to elaborate? Why do you think it is a function? And Anurag, would you be kind enough to tell us why do you think it is not a function? I'm not seeing any answers, guys. I mean, it's not going to be a yes or no answer. I'll be asking you counter questions for sure.
an explanation. Just explanation for yes and no.
Yeah, we just want some explanation. Every input has output. Does every input have an output in the first case? Or am I missing something there? Jagdish? In the first test case, right.
Got it. So he says that there is an output for every input.
No,
Is this
he's
what you
understood
get?
it. He's understood. Yeah, few inputs are missing. That is true. That's why the
Okay.
first function is not even a function. The first case is not even a function. So forget about on to or 1-to-1. It's not even a function. So the first is not function. Let's move on to the second one. Is second one a function? Pratmesh says yes. I believe Pratmesh.
It
Let
is.
me. Okay. It is. Shriram says yes as well. Okay. Anyone give me a reason. Why do you say yes? Quick reason. Shriram?
All the domain is mapped to one any at least
I do
one.
not know what is domain.
Yeah, me either.
Okay, all the inputs have at least one output that is mapped to it. So
Hmm.
that, and then one input doesn't give
Oh,
one.
oh no, 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 no. Yeah, that is right. One input does not give two outputs. That multiple outputs. That there is no ambiguity in the outputs. Right.
Yes.
Right. 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 Every input has an output. Correct. Every input has an output, and no two inputs have. Sorry. Not a single. You don't
No
have two outputs for a single input.
input.
Okay. That's another condition for a function. That every input should have an output and no two outputs should have a single input. That means you should not have any ambiguity of the output. If you are putting a orange in the juicer, you should get an orange juice, not a orange juice and a watermelon juice. Shouldn't be ambiguous. Just one output. So is this a one-to-one function? No, that's another question of mine.
Better explanation would be that we have got a machine, for example, to get flour out of wheat. It cannot happen that one day you input wheat into it and get a flour, and another day you input kind of fruits in it and get juice. This cannot happen. No, you input fruit in it and you still get a flour. So this could not be, this makes no sense. As we discussed, function is a black box kind of machine. You give it
We were
input, you get
actually
output.
we were actually talking about one single output giving you two outputs at the same time. So
Single input giving two outputs.
that's two input. Yeah, inputs giving you two outputs is not a function. That's what we were
Okay.
explaining there.
So
Anyway,
it gets
we'll
more
continue.
interesting. You give flour once and get flour. Input wheat once and get flour, and then you input wheat the next day and get juice.
No. You put in wheat once and you're getting two outputs at the same time, not one by one.
Okay.
That's the thing. Anyway, we'll continue from here. So
It
is
is
this a
bringing you a
one-to-one
dove
function?
itself.
Is this a one-to-one function, guys? Yes. Pratmesh says yes. Pratmesh, can you tell me why? Can you tell me why? Every input has exactly one output. That is correct. That is correct. So this is a one-to-one function. And Prathamesh has also told us that every input in this has one output that is unique. So there is no two inputs mapping to one single output. So it is one-to-one. Is this a onto function? Is this an onto function? Anyone? Quick answer. Himanshu, Jagdish, Jagrit.
No, it's not.
Okay, it's not. Okay, why, Shriram? Why do you think it's not?
Because not all what is that elements in the range is mapped to the codomain. Like sorry, mapped to the input.
What is range? I don't know what is range.
Okay, not all the balls in that second box is mapped with the first one.
Right,
Hmm?
right. That is there. Not all balls in the second box are mapped to some ball in the first box. That is correct. So it's not a onto function. What about this function? Is this a function? First of all, is this a function?
For every input, there should be an output. Is it the case?
Is this a function? That's my simple question. Guys, Himanshu says
says
no.
no.
Care to elaborate why, Himanshu? Why do you think it's not a function?
For two inputs, you are getting the one output.
Well, you can have that.
No,
What
for two
about
inputs.
Yeah.
y is equal to
Maybe
x square?
Oh, okay. Yes.
For one input, you shouldn't get two outputs. But for two inputs, you can get same output. Right?
it's like because he used the example of orange juice, like even if you're like the size of the orange is different, you'll get the same orange juice probably, right? Yeah.
Correct. That's correct. So yeah, that's a good example, Jagdish. X square. X square is such function. Right. So we are getting, so it is a function, right? We saw that okay, all the inputs have some output in the second box, and no two outputs in the second box have one single input. That means there is no ambiguity about the output. So it is a function. Is this a one-to-one function? Is this a one-to-one function? No, it's not. Pratmesh says it's not. One to many, correct. That's true. For one input, we are getting no unique output, right? There are two inputs in the first box mapping to one single output. That means it's not one to one, it's two to one, right? So it's not one to one. Is it an onto function? Is it an onto function? Guys, Jagdish. Okay, yes, Jagdish says yes. It is an onto function. Jagdish, can you tell me why it is an onto function? All output has inputs. Correct. That is true. So all the balls in the second box are mapped to some ball in the first box. And that is all I need. For onto functions, that's all I need. I do not need uniqueness in the onto function. I talk about uniqueness only when I'm talking about one-to-one functions, not when I'm talking about surjective functions or onto functions. In onto functions, I can have two inputs mapping to a single output. As long as I all my elements in my second box are mapped to some element in the first box, my condition is fulfilled. It's onto. Let's look at the next case. Is it a function? The next case. Is that a function?
Anurag says yes.
Okay. And
What
Raj
else?
says yes.
For a input, there is an output. I guess it would be a function.
Yes, one to many, not onto. Okay, we'll see. We'll see.
One to many.
More like many to one.
Hmm.
Think about it, Prakash. Right? Yeah. Anyway, so this is a is this a function? Pratmesh says yes. Anurag says yes. Yes, this is a function. If you take a look at it, we have all the inputs mapping to some output in the second box, and no two outputs are mapping to a single input in the first box. It is a function. Is this a one-to-one function? Okay, somebody said yes. It's a one-to-one function. Care to elaborate more? Why? Why do you say it is a one-to-one function?
Is there a unique output for every input?
Why do you say it is a mistyped? Okay, no issues, no issues. So
Okay.
what do you think is the answer? Is this a one-to-one function or is this not a one-to-one function? See, you have confused me, my friend. We'll have to clear this confusion now. Okay, Ashik has joined. Okay. Is this a one-to-one function? Anurag, you were saying something. I'm not able to hear you. Can you type in the chat? Is this a one-to-one function?
Hello, am I audible?
Yeah, perfectly audible now.
Okay, it should be two because the domain has a unique.
Okay, not one-to-one, says Jagdish. Yeah, Anurag, can you repeat that once again?
So I was saying is that the domain should have a unique.
I don't know
I don't know
what is
what domain
one-to-one.
is.
Domain may
I
put.
I don't know what domain is.
I know input, I know output.
Yeah,
Okay,
input output.
the input has a input.
Okay, your voice is a bit muffled.
Okay, so
Jagdish, care to explain why do you say that it's not one-to-one? I'll come to one-to as well, but why do you say it is one-to-one? No, sorry, why do you say it is not one-to-one? Many to one. That is right. That is right. So, do you see that there are two inputs in the first box that are mapping to one single output in the second box? So, it is the uniqueness condition fails. So, it is not one to one. What about on to? Is this on to? Curious. Is this on to? Till now, what we saw was if it one to one, it was not on to. If it was on to, it was not one to one. But is this one to one or say is this on to? Anurag says no. What about others? Jagdish also said that it's not on to.
Has somebody got a counter?
It's
No,
not.
Pratmesh, Pratmesh
It's not
also said
on.
not. Yeah. Why Sriram? Why is it not on to?
Because again, not all balls in the second box is accounted in the first one.
Perfect, perfect. That is right. That is right. Maria, can you do one thing? Draw another ball in the first box. In the same example, draw one another ball in the first box and map it to. Oh, sorry. Not in the first box. In the second box, draw another ball in the second box and map one of the outputs to that. One of the inputs to that.
1 second, sorry.
No issues. Take your time. Yeah.
Yeah,
Map one of
what do you
the
want me to do?
map one of the inputs to this ball.
बहुत खतरनाक चीज की है.
Just map one of the inputs to this output. Okay, perfect. Tell me, guys, is this a function?
अरे one
Pratmatious,
to
no?
ask whether it is 1 1 or on 2. Why are you asking it as a function or not?
We'll
Let
see.
others let other answer na.
That's yeah. Is this a one-to-one function? Is this a on-to function?
So which function is it? 1 1 or on 2? This should be the question. Now with the new changes, this is 1 1 function or on 2 function or both? Somebody please.
Better you just delete this ball. You just deleted this ball, Maria, and we already
Anurag
have
says
had
just
one ball,
on 2.
right? Yeah, just
Anurag says just on 2.
coming to that. Maria, just delete this ball. Just map to the
And
existing ball. Just delete. Just a second. Just a second, Nishan. Just a second. I'm making another change to it. Just map the this ball to that existing ball. Same input to that existing ball. Oh no. Not the same. The empty ball where there is no input is mapped. I want you to map to that ball.
Okay, can you tell me again? Like, you want me to add an extra ball here?
No. I don't want you to add an extra ball. We already have an empty ball there, which is not mapped to anything. I want you to map. Yeah, I want you to map one input to that.
Okay, bad drawing skills.
No issues. Take your time.
There were 3, right? Yeah.
Yeah, I mean, it would be better if you map that to the empty ball instead of mapping to the first ball instead. Yeah, and also to the. Can you also map it to the existing ball that it was mapped to?
This is mapped to 2, right?
Yeah. Right. Perfect. Is this a one-to-one function or is this an on-to function? Can anyone tell me? Is this a one-to-one function or is this an on-to function?
How about both?
How about both? Okay, interesting.
Which one? No. The one. Okay, sorry. No.
Just got off of
I saw the
both.
wrong one.
Are you taking Chetan for his tone?
No, just a second. Bharat, we are actually discussing functions. Fourth question of linear algebra 75. Yes, correct. Was this fourth? No, it's actually the
Third question.
third question.
Good.
Third question.
On to
Guys. Just Bharat, it's third question of linear algebra 75. Yeah. So what do you think? Is this on-to function or is this a one-to-one function, Bharat? Is this a one-to-one function or is this an on-to function? No. Second last one, Bharat. Is this a one-to-one function or is this an on-to function? The question is the same for everyone else as well. Maria, draw a ball. You have erased one.
Oh yeah. Okay, sorry. The eraser is pretty big. Yeah. These
Not
two
a
lines are
function, says Himanshu. Okay, no, he says not a function.
Function ही नहीं है.
बताओ.
And the question is 1 1 or on 2?
Not a function. One input cannot have two outputs. Okay.
So one input has 2 outputs.
Yeah, that there is a input that is mapping to two outputs. That is correct. So it's not a function. So there is no point in asking the question, is this a one-to-one or on? Okay, So you guys have understood this point. Second one is not a
So,
function.
so
Right.
it was like we are inputting apple and we are getting lassi and apple juice both at once. Okay, man. This is not
That
possible here.
correct. That
This
is
is
true.
not possible. This is
You
not
can
possible.
only get an apple juice by inputting an apple. Okay. Let's move to the last one. Is that a function? The last one, is this a function? Says yes, Anurag. Bharat says yes, it's a function. Himanshu says yes as well. Pratmesh says yes as well. Okay. That's a function because every input is mapping to one output in the second box, and no two outputs have the same input in the first. That's true. Is this a one-to-one? Okay, you've already taken much. Is this a one-to-one function?
I could
No,
be
it's
wrong.
okay. It's fine.
I could be wrong. Feel free to
Himanshu,
correct us.
Himanshu says yes, it is a one-to-one.
See the frequency.
Pratmesh.
See the frequency of answers which are now coming. I'll give you 3 cheers for the effort you put, Chetan. You know, nobody explains like this. I've never seen anybody explaining like this.
Thank you. So it's a one-to-one function, okay? Because every input is mapping to a unique output in the second box. That is true. Is this a onto function now? Is this an onto function? Guys? Yes, it's an onto function.
Why is
Okay.
it?
So the catch in the previous question was that Chetan asked you whether it is 1-1 or 1-2. Can you scroll up, Maria, once again? So the catch is that when somebody asks you whether a function is 1-1 or 1-2, first you have to check whether it is a function in first place or not. Then go for checking it is which kind of function. Always check whether it is a function or not. Okay. Okay, we can move ahead, I guess.
Yeah. Okay, let's
Like,
move to
just
the
make a general conclusion. I mean, what you said yesterday.
yeah. Okay. Let's just I'll summarize everything. So first, when you get a function, right? When you get a relation, any sort of relation, from the first case is tan's a function.
Tan x
Is
is
okay,
talking about.
tan x a function. Is tan x a function? As at input 90, it gets an output undefined, tends to infinity. Okay, I'll come to that, Him. I'll come to that. So let me summarize it. I'll answer this question. Actually, I was hoping that Rishabh was here because Rishabh asked me the same question yesterday. I couldn't answer this question. Anyway, so let's first think about what a function is. A function is a relation. It is some thing that we give it in input to, and it gives us an output. What is the unique thing about functions? The unique thing about functions is they take all inputs and they map those inputs to some output. They don't neglect any input. They don't reject any input. They accept every input.
फंक्शन
Okay.
कभी बुरा मान करके बुरा नहीं मानता है
ना नहीं बोलता है.
ना नहीं बोलता है कभी
It
it
doesn't
never
say no
says
to
no
you. It doesn't say no to you.
it always
So
gives you an answer
yes, it also always gives you an answer. That's a function. So another thing is it does not uh, give you ambiguity. So when you ask the function, are you free tomorrow? It doesn't say maybe. It will also always say yes or no. It doesn't say maybe. If you ask the function, let's go on dinner tomorrow, it doesn't say we'll see. It will say yes at 9, or it will say no. It doesn't keep ambiguity, unambiguous. So it tells you this is the output. Okay. So for every input, you will get an output. But for every input, you will not get more than one output. Okay. So that's a function. When you talk about functions, the first thing here that you need to do is You need to define the domain and the codomain of the function. What is domain? The first box represents the domain and the second box represents the codomain. What is domain? Domain is the set of all inputs. All inputs that you're giving to the function. That's your domain. What is codomain? All the possible outputs that you can get from the function. Possible. Keyword being possible. Not the actual output. Possible output.
That is
That
Sambhavit
is
Parinam.
right. You'll have to translate it in English for Maria. Okay.
All possible outputs.
So that's your codomain. The second box represents your codomain. Okay. You probably won't get all the outputs, but those are your possible outputs. So you first need to define what is your domain and what is your codomain when you're talking about functions. Only then you can talk about what is the actual output you are getting. That actual output that you get is your range. And your range lies in your codomain because it's part of the possible outputs, right? The outputs you will be getting will be part of the possible outputs. So your range is part of the codomain. So that is domain, codomain, and the range. So first you need to see if it is a function. If it is a function, then define a domain and codomain for it. Figure out what would be its range. Then, after you figured that part out, look at whether it's one-to-one or an onto function. If it is both, you call it bijective function. That it is both one-to-one function and onto function. One-to-one says for every input, you will get only one unique output. You will not get a same output for any two inputs. That's one-to-one. For two outputs, you will get two separate unique outputs. You won't get a same output for two inputs. That's one-to-one. Onto is when all the elements in your codomain are actually mapped to your some elements in the domain, some input. So you will get all possible outputs from the codomain. That's your onto function. And when you have both the conditions satisfied, that's your bijective function. So that's a bijective function, right? Okay. So I said that your function will accept every input. It will not say no to you. It will not say no to you. It will not uh, reject any input. But Shame said that is tan x a function? Because at 90 degrees, if you input 90, uh, it gets the output undefined. Another example I give you is, can you write it down, Maria? X by x minus 2, not defined at 2, right? X by x minus 2, not defined at 2. You can take, it's easier to visualize in functions in fractional form because you know that your denominator cannot be 0. Also, root, under root, right? X minus 2, another function that is not defined for all the inputs in real domain, right? Are these functions? Now, this was the question that Rishabh asked me yesterday. Is this a function? Are these functions? Can anyone tell me? Are these functions? Because I said that function accepts all the inputs. It doesn't say no to you, but these functions say no to you. These functions tell you, okay, I'm not going to tell you the answer for this. Undefined. Are these functions? Can anyone tell me? Are these functions? Anyone?
It
Where is
depends on
the
the domain, right?
Pardon?
Yes, Sriram.
Depends on domain.
Can you repeat that?
You're
It
saying
depends on the domain that you take, right?
No, I'm taking all reals. All reals.
Then no.
Okay, but these are functions. You treat them as functions. For tan x, x
Then
can take
you
any
should
value, so it's a function.
you should
But
take
Jagdish came said that for tan x, 90 degree is not defined, right? Tan 90 is not defined, undefined. You don't have slope for 90 degree, right? It can take any value except 90. But I said that your function doesn't say no to you. Yes, Shriram, continue. You were saying something.
wait. So yeah, exactly right. You have to take anything but tan 90 and
Mhm.
the multiples of it. Similarly, for the second function, you can take any other value other than 2
Mhm.
because it's not defined at 2. So for the thing was that
Are these functions? That's my question. I know where they are not defined. I know the answer. Are these functions? That's my question.
there are functions in places other than these points where they are
No,
not
no, no,
defined.
no, no. That's not a satisfactory answer, Shriram.
Let me
Like,
drop it.
just try to answer the question. Is it a function from real numbers to real numbers?
Just a second. Yeah, these are functions from reals to reals. These are functions where domain is reals and the codomains are real. Are these functions? You've been studying these as functions, right? In your high school, in your Maths 1 course for IITM students. Are these functions?
so Jagdish says that for tan x, x can take any value, so it's a function. It's
It
a
cannot, it cannot.
discontinuous
That
function.
I also already answered that. It does not. I already answered that. So okay, let me answer this. These are actually not functions. These are in fact not functions. These are what we call as partial functions. These are called partial functions. Partial functions are such functions that are not defined for all the inputs in your domain. These are not true functions. So I hope that answers your questions for tan x him. I hope that answers it.
Similar example would be, stepwise
Okay.
functions.
Yeah,
And many more.
stepwise functions. That's correct. That's correct. Another example. But stepwise functions are defined for every input. They're defined for every input. They're discontinuous, but they're defined for every input. So they are functions. So yeah. So these are actually partial functions. If you want, I can elaborate on that a bit more once we are done with our discussion. But these are called partial functions. Partial functions are such functions which are not defined for all the inputs. These are like your friends. Ambiguous. Do we have a plan tomorrow? Maybe. These are partial functions. So your friends are partial functions. Okay. But true functions never say no to you. Those are your best friends. Call them at night. Never say no. So that's functions and partial functions. Okay. Let's move on to the next question. Next question is going to be pretty fun. I think it's going to be pretty fun. Can anyone tell me a function from R2 to R2? Give me an example from a
What is
function.
R2, Chetan?
R2. Okay, yeah, I'll explain that. Okay. R2 is okay.
First of all,
Okay,
tell
let
them
me.
what is R1, na?
Yeah, yeah, yeah. Okay. Can anyone tell me what this notation R means? What is R means? What does R mean? Real numbers. Perfect. Perfect. Real numbers. Right. Right. Right.
Runs is scored by
So.
Virat Kohli.
Yeah.
Then
They
they are
So
also
eventually
real
cover
numbers.
the real number domain, I guess.
So these are
I
real
think
numbers.
runs code are not real numbers. I mean, runs code is not going to be a real number because it's only going to be an integer. Like you
That
you
was a
don't have
joke.
half
That
of
was a
it.
joke.
Integers are
Yeah.
also subsets of real numbers, no?
Yeah, integers are also negative is also not possible. Yeah.
But you don't call them real numbers. You call them integers because they don't satisfy all the properties for real. Anyway, so these are real numbers. That's quite true. What does R2 mean? R2 mean that you have taken the Cartesian product of R with itself. What is a Cartesian product? Oh yeah, Anurag, I'm coming to two dimensions. I'm coming to that, but you should know why we call it two dimensions. So R is one set of reals, R is another set of reals. I'm taking the Cartesian product of that. What is the Cartesian product? Can anyone tell me? Anurag, you should be able to answer that. You had your qualifier
First of all,
recently. So,
ordered pairs. Ask them what is an ordered pair.
oh Nishan, you basically gave the answer, my friend.
Sorry.
I
But like
was
maybe
hoping and
someone can just it's like
yeah,
since these are all kind of basic things, maybe someone can explain quickly so that
yeah.
like we'll
So
try
we
to
can move
cover
on.
more ground.
Yeah. We can move on. Can anyone
Yeah, so
quickly
like
tell me what is a
whatever
Cartesian product?
understands, maybe just list an example so it's pretty clear that you actually have an idea.
Just a second, Maria. Anurag,
Example
can
of
you answer this? Can you answer this? Just a second, Maria. Can you answer this? What is a Cartesian product? I am pretty sure it must be clear to you. You had your qualifier recently, so should be clear, fresh in your mind. What is a Cartesian product? No answers? Set of all ordered pairs. Oh, that is correct. That is correct. So you have two sets. You're taking set of all possible ordered pairs. What is an ordered pair now? Ordered pair, since the name suggests, it's a pair. Okay, it's a pair. So a pair, that means two. So you're taking two elements from two sets and you're making a pair out of those. And since it's ordered, you know the first element is coming from the first set and the second element is coming from the second set. So that's called an ordered pair. And set of all such ordered pair, all, okay, that's called the Cartesian product. So we have one set 1 comma 2, we have another set 2 comma 3. We took the Cartesian product of this 1 comma 2, 1 comma 3, 2 comma 2 and 2 comma 3. This is my Cartesian product of these A and B. Now think about it now. I took all the real numbers. That means irrationals, rationals, integers, fractions, uh, natural numbers, everything. I took all the real numbers and took Cartesian product of that. What I will get is some x comma y as the sort of general notation for that Cartesian product, where x comes from R and y comes from R. Okay, that's the general notation for this. X comma y. Since I have 2 points, I can actually now represent 2 dimensions with these. These can actually represent point in 2 dimensions. That's why we call it R2. We call R2 2-dimensional plane. We call R 1 dimension because you only have 1 dimension in it. Only reals, 1 point. You have 2 ordered pairs, 2 ordered points. You can represent all the points in R2. That's your R2. Similarly, you have R3 as well, where you have X, Y, and Z ordered pairs from R, real. That is 3 dimensions, and you can go till Rn. Okay, that's the general idea of a Cartesian plane and what is R2. Okay, can now someone tell me what is the function from R2 to R2? Give me an example of a function from R2 to R2. Guys,
See, if it is the function, it will take input and it will give it an output.
right. Give me some example from R2 to R2.
Okay. Like if I'm taking f of 1, 2, it could become 2, 4.
2, 4. Okay, that's
That
like
is to say, if I'm taking input of 1, 2, it is giving me an output of 2, 4.
yeah. That's an input output, but I was asking a function. That's the input output pair, but I'm asking a function. That's not a
Okay.
function. That's an example of input output to a
Okay.
function.
Okay.
Guys, anyone? A function from R2 to R2 that takes output from 2 dimensions and give you, sorry, that takes input from 2 dimensions and give you an output in 2 dimensions. F of x comma y equal to f of x plus y and comma y plus 2. That is true. That is correct. That is one such function in R2 to R2. Equals to f of, no, it's not f of x plus y.
Equals
It will
to,
be
yeah.
x. It will be x plus y comma y plus 2. You cannot have the function as the as the output, right? You will have something. So if it,
It might have been a typo. It might have been a
yeah,
typo.
I think it was a typo. We have another. Himanshu says f of x comma y equal to f of y comma x. That is one. That's right.
Okay.
Literally f of xy. This was the
Okay.
other example
We
in the
have
chat.
f
Do
of
it.
xy equals to x prime comma y prime. X dash comma y dash. Okay, that's another function that we have.
Yeah, yeah,
So
sure. Like,
yeah, so we have these functions, right? Now let's move to the question number 4. Okay, it says that give an example of a very nice function. Maria, can you show that? Can you show that once again? Explain what is so nice about your function. Why should one study such function? Okay. Okay, I think this is that game question. So let's play a game.
Where is this question? Question number 5.
Question number 4. Question number 4.
mhm.
This is a game question. Let's play a game. You give me two inputs. Two inputs. I'll give you outputs for those, and you'll have to tell me what is the function. Okay. Are you guys ready?
No, one second. First of all, let us take some examples. Three examples we got for function R2 to R2 function, right? Let us illustrate it with examples. For example, take f1, 2. F of 1, 2. We have got a f of xy is equal to x plus y comma y plus 2. Let us write input and output. And then
I
say
didn't
that
get
we
you.
have,
I didn't get you.
I'm talking about the examples, 3 examples, which is written below the blue line. That is function from R2 to R2.
Yeah, we already have the examples for functions, right?
No, what I'm saying to make the thing make this game more crystal clear, I'm saying that let us give it an example.
Oh,
Like
okay. Maria, click one example of 1 comma 2 for the first one. You will get.
What are we getting as an output? Correct.
Yeah. Okay. Can you take f? Oh, yeah. This is for the f of x comma y equals to x plus y comma y plus 2. So the output would be 3 comma 4.
Right.
Okay. This is
Okay.
the
What about next one? F of x comma y, take f of 2, 5.
Yeah. So take Maria f of 2 comma 5. F of 2 comma 5. It will give you 5 comma 2 for the second one.
So we are seeing how we are operating here. Fine.
Yeah.
There is some sort of thing going on that is well in front of our eyes. We're giving it an input and we are getting the output. I guess nobody is having problem at this point of time. I hope so.
Yeah, so the game is like you guys don't know what the function is. It's like maybe like it's not exactly 20 questions. I tell you, I mean, okay, think of it as this is some like your function is something. When you apply orange, you get orange juice. So what is it? It's a mixie. So you don't know it's a mixie, but we'll tell you that if you apply orange, you'll get orange juice.
Hmm.
That's like you give any input you want, we'll tell you what the output is, and you have to guess what the function is.
Correct. That's the game. You tell me two inputs, I'll give you two outputs. But then the deal is you'll have to guess the function. If you ask me more inputs, I'll give you more outputs, but I'll change the function. The function won't remain the same. I'll for one function, I will only give you two outputs. And then afterwards you'll have to guess what's the game. What's the function. That's the thing. Go ahead. Guys, ask me.
Somebody give Chetan an input, he'll give you an output.
Right.
Chetan is a mixer, kinda.
I mean, I would have preferred
mix?
computer G, but
Who does mixing? Who does mixing with numbers? Mixing of numbers.
right.
Let us see how
So
mixes things around. Okay, somebody has given 1 1 and 1 0. Great. So let us go with 1 1. What
okay,
output do you give, Chetan?
-1, 4.
Okay. Another somebody has Imhanshu says 1 0.
-1.
1.
Just -1.
There are two.
Okay.
-1, -1.
No, let Chetan answer. No.
What?
So
This is
I've already given they've asked me two inputs. I've given two outputs for that. I'm asking for a function now. What could be a possible function?
So no, let's see the screen. Maria has written f of 1 comma 0 is equal to -1 comma -1. Is it fine?
No, it's -1, 4.
4.
Sorry, -1, 0. -1, 0.
0. Okay, so 1 1 was given by Jagdish. So you have now to guess the function, Jagdish. What is the function? How 1 1 become -1 comma 4? As previously 1 2 was becoming 3 4 and 2 5 was becoming 5 2. We knew the relation. It was well mentioned. Now the relation part is gone. Tell me. क्या चल रहा है? Jagdish says -x comma y plus
Oh,
3.
sorry. No. This is incorrect. Sorry. Let me tell you the output just a second.
Okay. Chetan is making some corrections. Pardon, Jagdish. Really
Yeah.
sorry.
So for the first one, it's -3
Okay.
and
Chetan has
-3 comma -3 comma 3 -3 comma 3 for the first one, and for the second one, it's 2 comma -1. 2 comma
Okay.
-1.
Now
And
Jagdish is supposed to establish a relation. Okay, he has established it straight away. He says
-3x comma -3y.
3y.
Does this satisfy it? If we input 1 comma 1, it gives me -3 comma 3. But if I input 1 comma 0 to it, what does it give me?
One second, I'll be back. Yeah.
Yeah, okay.
Are you getting the point, Jagdish? See, It has to satisfy both the conditions simultaneously. You have to tell a function such that when given input 1, 1, it gives -3, 3, and the same function, same machine should give 2 and -1 as well.
Well, not same machine, but yeah, I mean, it's a function. It's a function which has two, which gives you two outputs or two inputs.
Yeah.
It can be broken down into other things as well, but yeah. Tell me what should be what can be the function.
Guys, come on.
Some encouragement from Ankit.
Yeah.
Guys,
Sri Ram, Himanshu, Jagdish, HEM, GVK. Who is gone? Bharat, Anurag, Dubey, Prathamesh.
tell me what can be function? What can be the function? Guys, okay, no issues, Shriyam. Okay, no issues. So we'll write down the function. So can we put it on the form of matrix to solve? I mean,
Right,
you
like this thing. For the first one, 2x minus 5y, comma, 2x minus 5y, and 5y.
Maria, 2x comma 5y comma
2x minus
minus
5y.
5y comma
Yeah, just check this thing out first. Does it
comma.
satisfy both the inputs?
It will satisfy the first input, that is, it will give you -3. What's the second part of the function? It's only one part of the function.
Yeah. I'm checking first. Let me check it if it's correct. If I go 1 0, then that gives 2, and 1 1, then it gives us -5. Okay. Second, I need to think. Just
What is written it? Okay.
yeah. 1 1 1 sums 3 means 2 and 1. It's,
3y minus 1.
Maria
yeah,
is
it's
trying to solve
minus x
4y
plus
minus
4y. Yeah.
-x plus 4y. So if
Yeah.
I give it 1 as input, 1 and 1, it gives me uh, 3. And if I give it 1 and 0, it gives me -1 and 0. Right. This is one such example. Let's write down another example for this. Maria, can you write down 2x minus 5y, comma 2x plus 4b, comma 2x plus 4b, 4y, 2x plus 4y minus 3. See if it satisfies both the conditions.
No, it does not. When we put 1 1, it gives -3. It should be +3.
1 1, if you put 1 1, it gives you 3, right?
Well, oh yeah, 4, 5, 6 minus 6. Yeah, 3, 3, 3. Sorry. Yeah,
And if you give it 1,0, it gives you -1,
-1. Yeah, it satisfies. Yeah.
right?
Yeah.
So
Yes.
can we say that there are infinitely many possibilities for such functions? That if you that infinitely many possible functions can give you the same output for the same input. Can we conclude that? Can we conclude that there is no one single answer to these? There can be multiple answers. One example was given by Ankit. Another I gave.
Let me give some visual hint to this, problem at our hand. For example, Chetan lives at Bombay and Ankit lives at Delhi. So Chetan wants to go to Ankit. So prima facie, input is at Bombay and output is at Delhi. Chetan, so what he basically did presently, I'm telling you this. So Chetan asked everyone, I want to go from Bombay to Delhi. What should be my, which path should I tread? Which train should I board? So different people give different ways, to Delhi, from Bombay to Delhi. Somebody says, why don't you just hire the next generation bullet train? Somebody says, okay, aeroplane ticket is cheaper than bullet train. Somebody went into future and told that, okay, I'd prefer going through what is called vacuum bullet train. I'm forgetting the name.
Hyperloop.
Hyperloop. I suggest you go via Hyperloop. Anyways, jokes apart, many ways were kind of suggested. Go via IT Roper, go to Punjab, then go to Delhi.
That's going to be a long route.
Somebody said, why don't you take a tour to IT Madras first and then get and go to Delhi afterwards via plane. Okay,
Right.
and many such permutation and combinations. That is to say, there were many ways from an input to output. So this is what that's why don't be startled to see that, okay, one input is many things are giving the same input and output pair. Yes, that should be the case. That is what Chetan wanted.
And Rag says that one displacement and infinitely many distances. Haha, that's true.
Correct.
That's another way to put it. A nice way to put it. That's good. That's
nice.
Quite true. Okay. Let's then. What are nice functions? Can anyone tell me what are nice functions? We have two sort of functions. We have two kind of functions written in front of you. One of them is the nice function. Can anyone tell me which one is it? Is it the one I gave you guys, or is it the one Ankit gave you guys? One of them is a nice function.
I've only written down two. Is there any other example?
Oh, no. The first one was given by Ankit. The second one was given by me.
Ankit did not suggest 4y minus 1.
Actually, I suggested 4y minus 1.
Okay,
and that is true as well.
Okay, no. Neither of these are nice
Nice
functions.
functions.
Yeah, that's why it was, yeah.
Okay, neither of them are nice functions.
So, I mean, anyone.
Let's think of another way. Let's think of another one. So 2x minus 5y, comma.
Yeah, we have an answer in the chat. So the answer is.
Himanshu, were you part of the yesterday's discussion by any chance?
Oh, constant. Okay.
Yeah. Right. That's right. So we don't have an example written here, but we consider nice functions as those functions which have the constant to be 0. Okay, which have the constant to be 0. For a second, I only
passing through origin.
Yeah.
Nobody knows origin for origin.
Right. So I mean, we consider nice function as those functions which are which are having the constant to be 0. Those are some nice functions. We call them nice functions. We'll talk about why we call them nice functions once we discuss couple more examples. It will be self-evident why we are calling them nice functions. Okay, let's move on to the next question. So the next question says that define a function phi from R2 to R2 which satisfies the following property. The point phi 2 comma 3 equal to 7 comma 4. Okay, 2 comma 3 gives you 7 comma 4. We just saw that there are infinitely many such possibilities. Can we get one such possible answer of a nice function which gives me 7 comma 4 once inputted 2 comma 3? 2 comma 3, 7 comma 4. Give me one such function that satisfies this. Go ahead, guys. I need one example. Only one. One nice function. It's easy. It's not that difficult. I mean, you only need to give me one such function. 2x plus y plus 1. That's correct. Y plus 1. Oh, yeah, right. 2x plus y, comma y plus 1. But it is not a nice function. I don't like this function. The one you gave me, Jagdish. 2x plus y is 2x plus y. 2x plus y is not satisfying my condition.
Yeah,
Can
4 plus
anyone
3 is
drop some-
7, right? Satisfying.
Pardon?
4 plus 3 equal to 7, right? 2 into 2 plus 3 is 7. 7. Yeah, it satisfies.
2 plus. Okay, yeah. 4. Okay, yeah. 4 plus 3.
2x plus y and 4 by 3y. That's it.
2y minus x. 2y minus x. 2y minus x. No. 2y minus x. 4 by 3y is
That's also
not.
correct.
No. I don't like that function. I don't like that function. Doesn't
But
seem that
Can
yeah,
nice
you
to
not
me.
like a nice function?
Doesn't seem nice to me. So
yeah,
You are
maybe,
changing nice
no,
definition. You are changing definition
no,
of nice then.
yeah,
no,
no question.
I'm not changing nice definition of nice function. We could
But
have
we
written that.
wanted coefficients in both the x and y. That's the only thing. Yeah. 2y plus.
2y minus x. 2y minus x. So 2x plus y and 2y minus x. Or you can say minus x plus 2y. That gives you this option. So we saw that my functions are nice functions if their coefficients are non-zero and their constant is 0. I'm considering them nice functions. Those are my nice functions. Okay. So after we've discussed this, we've observed that what are nice functions, what are the properties of these. Now let's move on to question number 6. Okay.
Yeah, like, can anyone suggest another example where you get the same thing? Just, yeah, like, I'll write an example maybe. You can
Write
check
down
if it's
5x minus y, comma,
Mhm.
uh, 3y minus uh, 3y minus no 2.5x. Does that work?
Yeah, that's yeah. This is also correct.
Oh, no. It does not. It does not, right? Does it?
9 minus 5, 4.
Oh, yeah. This is correct, right? So another example, 2.5x, right? Another such
So
example.
maybe, yeah, what's the general form of our nice function?
Yeah. Can anyone tell me what's the general form that we see here for our nice function? Guys? Okay, Rishabh has joined. I'll quickly go through one. Can you scroll to that function thing, Maria? Rishabh, can you hear me? Hello? Rishabh, are you there?
Yes, I'm here.
Okay. I have the answer for your question. We
Yeah.
discussed this in the today's session, but yeah, you weren't there, so I'm just repeating that quickly.
Yeah.
So tan x is one such example where your tan x is not defined for 90, right?
Yes.
X by x minus 2 is one such example where your function is not defined for 2. Root x minus 2 is one such example where it is not defined for any number that is from 0 to greater than equal to 2. Are you sure, Maria? It is defined for greater than equal to 2.
Oh, yeah, we are writing not defined. I'm
Yeah,
sorry.
it is not defined for anything that is less than 2, right?
Yeah.
Are these functions? Are
No,
these functions?
my question was not related to the function. My question was in terms of domains
Yeah.
and codomains. So does this value, as I'm
Mhm.
defining the function, that has to be a natural number. My domain is a natural number. So does
What do
that
you mean? What do you mean by natural number?
the natural numbers?
Okay.
So so then the relation which I'm going to form is then on those basis, will this be a injective, subjective or bijective or not?
Oh,
Like,
if you see, okay, let me explain that. If you are defined the domain as the natural numbers, okay, then none of these functions are functions themselves. If you define them as integers, the domain and codomain as integers, none of these functions are functions. If you define the domain and codomain as reals, none of these functions are functions. These functions are not even functions. You can't even talk about one to one or onto. These functions belong to a separate class, which we call as partial functions. Partial functions are such functions which are not defined for all the inputs.
Okay.
Functions are such relations which are defined for each and every input that you give them. Okay, they are defined for each and every input, but partial functions are such functions that are not defined for all the inputs in the domain.
Okay.
Does
That's
that
new.
does does this satisfy your question?
Yeah, I wasn't getting considering the partial function as a thing, so that
Okay. So we are actually taught in the high school that all of these are functions, but they are not actually functions.
yeah, basically I
They
solved get like hundreds of questions
hmm,
where we have defined the function in such
correct.
manners. So
They even ask you questions. Okay, what is the range for which this function is not defined, right?
yeah.
Right. But those questions are not actually related to functions. They are called partial functions. That's the correct term for that. So yeah, okay,
Okay.
let's
Well,
continue with yeah. Go ahead.
yeah, then I have a question related to the yesterday's what sir explained.
Mhm.
So there we were getting like A as a matrix, then eigenvector is equals to a new eigenvector. Okay, we were continuing that.
eigenvector as new eigenvector?
A eigenvector is equals to a new eigenvector.
He is saying
Oh yeah,
that
lambda times eigenvector.
Uh,
Oh
y-
sorry. Yeah,
no,
yeah.
what he is saying, if
n-
you are providing an input to a matrix, it gives an output,
Okay,
and
just a second,
sometimes
guys. Can we continue this discussion once we are done with the session? Can we do it?
yeah, sure.
Just okay. Okay. So, can anyone tell me what is a general form for these sort of nice function? What would be a general form of for these sort of nice functions? Anyone?
It's y equal to mx, or it's a line passing through the origin.
Ax plus by.
Yeah,
Yeah,
correct.
anything works as long as it passes through the origin.
It's like y equal to, yeah, okay. I mean, uh, see, y equal to mx is not the correct answer because
That's an
y
equation.
equal to mx is the equation of a line. Like, we're just asking,
Of a
that's
function.
not a form, right? I mean,
It's so okay. Let me clarify one thing. There is a difference between an equation and an expression. Okay, what we have here are not equations. Equation, by the name, as the name suggests, equation says that you're equating something to something else. That's what we mean by equations. What we have here is expressions. We are not equating these to anything. Yeah, we can equate the function, the entire function, to something. That okay, if I give this as the input, I'm getting this as the output. But these are expressions. What you see here, these are not equations. So y equals to mx is actually an equation. That's not an expression.
Yeah, other way to say it, as you have said it earlier, that it's a two variable thing, now
Mhm.
one variable, so we cannot
Correct.
assume line.
Right, right. So you gave the correct answer, Rishabh. So the general form for such examples for such functions is ax plus by, where my coefficients are not zero, but my constant is zero. So that's an expression for my nice function. Okay. So okay, moving on to the next question. The next question says, given an function phi from R2 to R2, which satisfies the following two conditions. That is, phi of u plus v equals to phi of u plus phi of v, and phi of alpha v equals to lambda times phi of v. What can one say of such functions? Observe this function closely. Such functions form the crux of several disciplines, mainly of sciences and engineering. Spend at least 20 minutes dissecting them to the best possible extent. Right? So, what were the two conditions that we got? Phi of u plus v equals to phi of u plus phi of v, and phi of alpha times v equals to alpha times phi of v. Can anyone tell me what do you know about these conditions? Can anyone tell me? What do you know about these conditions? Or what do you know about such functions which follows or satisfies these conditions? Anyone?
Just to push that these are the axioms of linear transformation. So it's a scalarity and additivity. So we are getting adding two vectors with each other, and we are scaling of one vector. So in both the conditions should be same.
Himanshu says
Scaling and
linear
adding.
Himanshu says linear transformation. This is not linear transformation, Himanshu.
These are axioms of linear transformation.
This is not linear transformation. When you combine these two, you get linear transformation, but this is not linear transformation.
Linear transformation will satisfy these conditions.
Correct.
Yeah, he's right. Yeah.
So you have a function.
Since we're talking about these nice functions, maybe
Mhm.
do you think the nice functions satisfy these properties?
We can check.
Okay, yeah. So we said that okay, we have the nice functions. We have our nice functions as ax plus by, right? That is my one such expression. Can can anyone tell me, do these nice functions satisfy these conditions? Himanshu says yes. Anyone else? Jagdish says yes as well. Shriram says
Yeah,
yes.
like why do you think I
Hmm.
mean why is your answer yes? So what essentially are these like, or maybe we'll discuss about uh, these functions that satisfy these, like someone said it's called a linear transformation. So yeah, so what do you basically understand from when you say linear transformation? And yeah, we actually started with matrices, and why are we discussing? It seems a bit unrelated, right? We're actually discussing about functions.
Okay, maybe not let's not touch upon linear transformations right away because it's an entire topic in itself. It will take the another 1 hour to explain linear transformations uh, from the basics. Yeah, but good people know about linear transformations. We're not touching them right now. They'll take too much time. Okay, can anyone tell me, okay, everyone says yes. Can anyone tell me why do you say that, okay, these nice function expressions satisfy these two conditions? Can anyone tell me? Maybe unmute yourself and yes. Maria, can you take over for okay?
Yeah, sure. Okay.
I'll be back.
So what we have these we were talking about nice functions, and we noticed that uh, these nice functions actually satisfy these properties. Phi of u plus phi of v. Second. So what can one say of such functions? Observe these functions closely, and they form the crust of spend at least dissecting them to the best possible perspective. So what is your like, yeah, so we have these two properties. So how do you think it relates to the nice function? Or like if you have anything you that came to your mind when you saw this. Someone mentioned linear transformations, maybe we'll not go into that. I can't check the chat. Yeah, sorry for the first one, but I don't know about the second one. Okay. Okay, you think the first property is being satisfied, but you don't know about the second one. Okay. Yeah, so let's just discuss about. So when I maybe we'll discuss a bit more about the earlier question. When I actually told you like about these not so nice functions, what we noticed is that we had an extra constant, right? So do you think these functions which have an extra constant actually satisfy uh, these properties? Maybe we'll just think about that. We talked about nice functions, then we talked about not so nice functions. So do the not so nice functions satisfy these properties? I'll check the chat. No, it doesn't satisfy. Right, it doesn't satisfy. Yeah,
Okay. Let's take one example for the not so nice functions. We wrote couple of them. Let's take one nice function. Can you take the nice function, Maria? Sorry,
Okay.
not so nice function. Not so nice function. Let's take one example, not so nice function. Then we'll see if nice functions satisfy or not afterwards. So we only need to check for these two conditions, right? We'll be checking these conditions.
So, okay. Should we conclude for today? I mean, how many participants do we have?
We have 10 participants. We'll be continuing the session. We'll wrap up by 11:30.
Sure.
We started pretty late. We started at 9:30, even 9:36. So yeah, let's just take one example for not so nice function. Can we get a not so nice function? Say 2x plus y, comma, minus x plus 3y minus 2. This is the not so nice function, right, guys? Let's input this in the function and let's figure out what are we getting out of that. Let's see if these are nice functions or not. Maria, can you input these and write down the whole thing?
What do you mean input these?
To the first condition, just write down the just show that if it's satisfying the first condition or
Yeah,
not.
so
Phi of u plus v, that is equal to phi of u plus phi of v. Phi of u plus
yeah,
phi of v.
yeah, just a second. Yeah, so your U is actually like some input, right? Yeah. So,
We'll write down input as well. Just write down phi of u plus phi of v equal to phi of u plus phi of v. Now, see this 2x plus y comma minus x plus 3y minus 2 is one example of an input. It's a general example of an input. This entire thing is an input. What we are doing here is we are taking two inputs, adding them up. That is, u is one such input and v is one such input. Okay. And we are saying then afterwards that if this condition is being satisfied. Okay, go ahead, Maria. Write down the whole thing.
yeah, so maybe we can write phi of
2x,
yeah
2x
3 comma 5, right?
Oh, you are taking example. Is it?
Yeah.
Okay.
So
This is only one input, right? You'll have to take another input for it.
this is u plus v.
Oh, this is not u plus v. You'll have to take two inputs for to prove that. You have phi of u plus phi of v. What are you going to do there?
Yeah.
Just take two inputs that
So
satisfy this
what is
condition.
phi here? Kedana? Are we going to define
Phi
a
is
phi?
just a function. Phi is just a function. Phi
Yeah,
is
but
just a function.
are we going to define it?
Not right now, not in this capacity, but you can, yeah, if you want, you can think of it as the matrix.
Now, if we want the output, then we need to define it. So otherwise, how
Oh,
we are going
function is,
to?
oh, no, we have defined the function. We have defined the function. Phi of x comma y is equal to 2x plus y, comma minus x plus 3y minus 2. That is phi.
Okay, so now what
Yeah.
is U and V?
Yeah, that's what. So you can do it in two ways. Okay, you can take two random inputs, say two random examples from that satisfy this condition, or you can do the general way. You can directly put this equation in that and see if it's satisfying that. I think the example would be much better because general equation would get too mathematical. So let's take x and y to be 1 comma 2. Uh, X and y to be 1 comma 2, and another x and y, another set of x and y, that is x1 comma y1 equals to be 2 comma 1. So this is the inputs, right? Now try inputting these in the function. So phi of u plus v, phi of u plus v equal to phi of u plus phi of v.
Yeah, sure. Phi is 3, 3, right? So
Yeah, this is correct. This is correct. Phi of 3 comma 3 equal to phi of 1 comma 2. What are you writing, Maria?
I'm applying this.
Oh, no. You're not applying this actually. Oh, no. Do one thing. Just delete this. We are not doing the equation thing. If you want to do that, you'll have to take that on the left hand side as well. This is not how you prove it. Uh,
Oh, we can actually do that. Like we can just take, yeah, we're checking if the left hand side and the one in blue is
Yeah,
correct.
even I
so
believe
let.
Gadana is doing the right thing.
Oh, no. Just do one thing. Tell me if I'm going wrong. Just do one thing. Delete this part. No, not the entire thing. Not the entire thing.
Yeah, I'll write
Part
it
of it
again.
was correct. Yeah, part of it was correct. So phi of 3 comma 3 equals to phi of 1 comma 2 plus phi of 2 comma 1. Yeah. Now
This is something we have to check. Yeah.
yeah, this is what we have to check. Now we'll solve right hand side and left hand side side by side. So this is phi of 3 comma 3 will give me what? What is the function, Maria? Can you take a look at it? 2x plus y, let me note it down. 2x plus y, comma, minus x plus 3y minus 3, something like that, right? Can you take a look at it? Minus x plus 3y minus 2. Okay, minus 2. So 2 times of 1. Why are you taking 1, Maria?
That's 3. Yeah, correct. Oh, yeah, I got confused when you, yeah.
I mean, either you can do side by side if you want, or you can take left hand side once and then right hand side
No,
once.
yeah, I
Mhm,
substituted in it in the,
mhm.
yeah.
Understood. So it is 2 times of 3 plus 3, comma, minus 3 plus 3 times of 3 minus 2. Okay, what are we getting? We are getting 6 plus 3, that is 9, comma, minus 3 plus 3 times 3, that is 9, minus 3, that is 6, minus 2, that is 4. So 9 comma 4. Let's check for phi of 1 comma 2 plus phi of 2 comma 1 as well. Okay. So 2 times of 1 plus 2 minus 1 plus 3 times of 2 minus 2. It's plus minus 1 plus 3 times of 2. So
Yeah.
it will be it will be 2 times of 1 plus 2, that is 4, and 6 minus 2 minus 1, that is 3. So Are we getting the same answer here, guys? Okay, no,
No,
just a
we
second,
haven't
Maria.
calculated.
Oh,
We
you
haven't
haven't.
calculated
Okay,
5
yeah,
of 2,
2 comma 1. Okay, I thought you were taking both of them simultaneously. Okay, so 2 times of 2 plus 1 comma minus 2 plus 3 times of 2 minus 2. So what are we getting here? That is 4 plus 1, that is 5, comma minus 2 plus 3, sorry, 3 times 2, that is 6, minus 4, that is 2. Yeah. So if we add these, we are getting 9 comma 5. 5 of 1 comma 2 plus 5 of 2 comma 1 equals to 4 comma 3 plus 5 comma 2, that gives me 9 comma 5. Now is this equal to my left hand side? What was my left hand side, Maria? Can you show me? 9 comma 4. Is this equal to my left hand side? Does this satisfy those two conditions? Guys, does this satisfy those two conditions?
No.
It doesn't, right? So can I say that my ninth functions are not satisfying those two conditions? Okay. Okay, let's take a nice function now. Okay. We'll do the same to that nice function as well. Let's
What is the difference between nice function and not so nice function?
okay, nice function, we define nice functions as those functions whose coefficients are non-zero, but their constants are zero. So you can have a function in 2 dimension in the form of ax plus by plus some c, right? And
Yeah.
we are considering nice functions as the functions which have the constant to be zero,
Okay.
but not the coefficients. I'll tell you the reason. Okay.
Yeah.
But continue, Maria. Can you take over?
Yeah, sure. Okay, yeah. So now we just check out the nice function. Like one example was phi of x comma y is equal to, I mean, for the calculation to be easy, x plus y comma x minus y. Right? So now we'll take the same examples that we took before. Phi of 3 comma 3 would be equal to 6 comma 0. Then phi of 1 comma 2 would be equal to 3 comma minus 1. Phi of 2 comma 1 would be equal to 3 comma 1. Now when we do phi of 1 plus phi of 2 1, we get 3 comma minus 1 plus 3 comma 1, which is equal to 6 comma 0, which is actually same as our phi of 3 3. Now let's check the second property also. Okay, so yeah. 3 comma 3, you can write that as 3 times 1 comma 1, right? So yeah, so our u is actually 1 comma 1 and our alpha is 3. I mean, I hope you remember this, what we had to check. These are the two properties.
Okay. So where were we? Did you define a function, Maria? A nice function?
Yeah.
Okay, x plus y and x minus y, right? And you took the examples as well. 3 comma 3, that is gives you 6 comma 0, and you added them. Okay, it gives you 6 comma 0, right? It satisfies the condition. Correct. So do we see that it satisfies the condition? Can we now think
The second condition.
why we set those expressions to be expressions of nice function? Do you see now why we call them nice functions? They are behaving very nicely. They're actually satisfying these two conditions. And the not so nice functions, they don't satisfy these conditions. They're not behaving nicely. That's why we call them nice functions. Okay. Is there anything else, Maria, you want to add to this?
Nothing else.
Okay. So let's move on to the next question. The next question says that consider R2. What are all the properties of this set? R2 is called a space of all vectors, aka a vector space. Look up for the definition of a vector space. Oh my God. Okay, this is that question. Okay, I'll have to discuss all the properties, I guess. Okay, okay.
I think we can conclude for today because it's
Yeah,
almost 11.
yeah, it's 11:30. I'll take up this question tomorrow, guys. The session officially concludes now, and we'll be continuing from here tomorrow, and we'll discuss the rest of the questions also. Tomorrow we won't go through question number 1 to this. We have discussed quite extensively, and we have made notes as well. We have notes. So tomorrow we'll be continuing from question number 7 onward.
Yeah, that's what I want to ask. Are you using an Android tablet or a writing tablet?
Maria is using the graphics tablet,
Oh,
Wacom. We have just used this dotted page. It looks nice to me. So I
yeah.
thought,
So I think then I can also shift to it next class, we said.
oh yeah. I mean, it's easier on my eyes just to, I mean, ruled lines are, I don't like them a lot.
No.
Just,
I just use them because I need to have that sense of direction because it's not
right,
like
right.
writing in
Yeah,
paper.
that's fine. Like, I guess those are all personal preferences. Like, you're
Yeah,
not expected to have, like,
yeah,
everyone would
right,
like
right.
it different.
Yeah, it's fine. I
Correct.
think dots still work for me anyway.
Okay. Today's discussion was more detailed than yesterday's one. I hope you liked today's discussion, Anurag. Nishan contributed quite a lot in the today's discussion, and Maria did a fantastic job. So all thanks to these guys, we were able to have a very nice discussion today. And thanks to Maria for all these notes. I couldn't have done without her. Couldn't have done this without her.
Yeah, that's fine.
Like
Good night, Anurag. Good night.
supreme. Yeah, thank you. So it looks like we are right now, able to carry on sessions even if Sri Vinay is not there.
Yeah.
But I miss him.
And
I miss him though.
Still, we do miss him, but it's not
Right.
like the session is dependent on him.
For
I want
me,
to see how we are going to do when we are going to we'll be in the last questions. So
right.
that's where
I
we are
mean,
going to
these
find
questions
trouble.
we already discussed. So, yeah, you
Yeah.
can stop recording. Did you record?
Oh yeah. Sorry.